Dean received his PhD in theoretical particle physics from Harvard University in 1998. Actually, that's when I started my graduate school. So in 2001, he joined North Carolina State University as a assistant professor of physics. He rose through the ranks and became a full professor in 2012. Since 2017, he has been a professor at RHIC. So everybody knows what is RHIC, right? The Facility for Rare Isotope Beams. That's the future for low energy nuclear physics at the Michigan State University. Dean actually have served and also currently serving in many important committees in nuclear physics. That includes the National Advisory Committee for the Institute of Nuclear Physics in Seattle. You know, if you want to apply for a program there, he will be reviewing your proposal. Has been a fellow of American Physical Society since 2014. In 2022, Dean was elected to the chair line of the Division of Nuclear Physics. That means he will be very important for us in the next few years. So Dean is a world-renowned expert in ab initio nuclear theory. Recently, he became interested in the intersection between nuclear structure and heavy ion, high-energy heavy ion physics. We actually together organized a very successful 5 weeks long program earlier this year at INT. Well, it is my feeling that he will be our best hope, okay, to get a reliable nuclear structure input for heavy ion collisions. I've seen this amazing pinhole picture where he showed how he can locate the position of all the nucleons before the collision, right? So today he will be delivering a talk on ab initio simulations for nuclear structure and heavy ion collisions initial states. As you all know, the presentation will be 1 hour long, approximately, and followed by a 30 minutes discussion. So take away, Dean.
Okay, thanks very much, Jiangyang. That was a very kind introduction. I look forward to talking with all of you. There's one motivation of my talk is to make this connection that Jiangyang was talking about, where we had a program and workshop at the INT just a few months ago, and a lot of you in the audience were attending. And there were many talks from the nuclear structure side, as well as from the heavy ion side, and many discussions, which I thought were very stimulating. And I'm very happy to have a lot of collaborators and friends in the audience from the heavy ion community. So there's something in the chat. Okay. All right, so let me tell you what the outline is of this talk. First of all, I'll give you a broad overview of ab initio methods for those of you on the heavy ion side who may not know some of these techniques. Then I'll narrow down to the lattice methods that we're using, what's called lattice effective field theory. Then I will talk about sort of what you can get from very simple interactions, the essential elements of nuclear binding. And then I'll talk about some work we did on the structure of oxygen and related to this pinhole algorithm that Jiangyang was mentioning. And then talk about ab initio nuclear thermodynamics, clustering in carbon-12, and this technique called wave function matching, which we're using for high accuracy calculations now. And then I'll just give a brief outlook. So ab initio methods have grown more powerful in the last, let's say, 15 years. So you can see the nuclear chart, things that have been calculated by years. And so you can see now we can get up to over hundreds of nucleons. And this is due to increases in computational power, but that's not the only explanation. It is also related to the use of renormalization, group methods, effective field theory methods that allow us to do calculations of nuclear structure with softer, more friendly interactions for the various many-body techniques that we are using. So let me tell you some of these techniques. So there is many-body perturbation theory. Probably most of you are familiar with what that is. That's basically doing a perturbative expansion, very often done in terms of connected diagrams. Then there's a technique called the in-medium similarity renormalization group method. And what you do there is you start off with some reference state, and then you consider some sort of like a Slater determinant, and then you have one particle, one hole, two particle, two hole, three particle, three hole excitations on top of this reference state. But what you can do is here's the many-body Hamiltonian, which connects all different sectors. The idea of the medium similarity renormalization group is to do a unitary transformation at the two-particle level that allows us to decouple the reference state from the other sectors. So this obviously will change the properties of the wave function, but this will preserve the energy eigenvalues. And if you want to calculate observables, you can then do the transformation on the operator observables themselves to recover that information. There is a technique called coupled cluster methods, which are, in some sense, are kind of similar to what I said for in medium similarity renormalization group, but these were actually pioneered first before a medium similarity renormalization group. And in this case, the decoupling is to decouple the elements of this column, this first column, such that the reference state has no other couplings along this first column. There is also this technique called self-consistent Green's function, where you take some state again, and you calculate the Green's functions, and you write down recursion relations, and you make some truncations up to, let's say, two particle, two hole, or so on, that allow you to then solve self-consistently for these Green's functions. There are calculations that are more sort of straightforward diagonalization techniques, where you take, for example, a harmonic oscillator basis, and you then simply diagonalize your Hamiltonian in that basis using sparse matrix methods and trying to do some extrapolations to infinite basis size. There is then the version of this, so this is what's called no-core configuration interaction. There's the symmetry-adapted no-core configuration interaction, where you try to do a little bit better by incorporating some symmetries of the harmonic oscillator. So the harmonic oscillator has an SU3 symmetry. And so what you can do is you can take representations of this SU3, or if you lift it up to a symplectic group, SP3R, you can capture more of the correlations in these, especially for the deformed nuclei, using this technique. There is these projected generated coordinate method techniques, either using what's called the Monte Carlo shell model, or just the GCM projected calculations, where you take some basis states, which may have, where you break some symmetries, like rotational symmetries and such. But this allows for you to capture correlations more efficiently, but then to restore the rotational invariance and parity symmetry by doing projections, and then diagonalizing and solving the generalized eigenvalue problem. Then there are the class of quantum Monte Carlo methods, where you use random numbers to sample the wave function of your many-body system, and then the distribution of particles or random walkers gives you then the wave function, right? And so the technique we use is lattice effective field theory, which is a quantum Monte Carlo method, but a fairly specific quantum Monte Carlo method. We take a lattice spacing of between, let's say, 0.5 to 2 Fermis. And so so it's different from lattice QCD. We're not resolving the quarks within the proton or the neutron, but we are trying to describe the correlations of the protons and neutrons with each other. And trying to describe things like superfluidity of neutron gases, trying to describe the structure of nuclei, of course, trying to understand the liquid-gas transition, trying to do nuclear reactions, both elastic scattering, as well as inelastic reactions and decays and things like that. So if you're interested to learn more of the details or an introduction to lattice-effective field theory, I have an old review now, but there's now a more recent textbook by my collaborators, Timo Lede and Ulf Meissner. So lattice-effective field theory is able to do an analysis of the strongly interacting phase diagram, approximately in this region here. So here's the on the horizontal axis is the density of nucleons in nucleons per cubic Fermi, and here's the temperature in mega electron volts. So we're not going to be able to reach, from our calculations, we don't reach the quark gluon plasma, which obviously is of great interest to many of the people in the audience here, because we're using the nucleonic degrees of freedom, and those are not probably the correct nucleon degrees of freedom, are not the correct degrees of freedom up here. But in this region, up to, let's say, 30, 40 MeV temperature, maybe up to twice nuclear saturation density, we can do simulations with this lattice-effective field theory. So you can see that there is a nice overlap with lattice QCD. So it's difficult to go with lattice QCD at cold temperatures beyond a certain angle of this phase diagram, because you hit this sign problem, which makes the cancellations between positive and negative configurations in your Monte Carlo sampling difficult to handle. Now, so what we do with these lattice simulations is we put chiral effective field theory on the lattice. Okay, so what is chiral effective field theory? So this is basically just expanding out the nucleon-nucleon interactions, or the multi-nucleon interactions, at leading order, or the most important interactions at low energies would be the exchange of a pion. So the pion plays a special role here in chiral effective field theory because, as I'm sure you know, in the limit that the quark masses go to zero, the pions are Goldstone bosons. And so they are light particles that give long-range interactions in that limit. So they're treated differently from everything else. But everything else is treated, all the other mesons are treated as some short-range interaction between the nucleons. So instead of having exchanges of rhos or sigmas or omegas, we have then some contact interaction that we don't resolve. And these are the leading terms in chiral effective field theory, the so-called leading order interactions. Now, if we go beyond leading order, then we have the more complicated pion exchanges like two-pion exchange, or more complicated contact interactions that are at next leading order, and so on. So we then tune these unknown coefficients of these interactions. So these coefficients will be dependent on our cutoff, how we cut off the high energy or the short distance physics. And they're unknown, so we have to tune them to reproduce scattering as seen in the laboratory with proton-neutron scattering, proton-proton scattering. And so here are the scattering phase shifts. Here is the spin singlet S wave phase shift, and this is versus the relative momentum in the center of mass frame. And so we can do the calculations at n next leading order, next to next leading order, or n3 LO, and compare them with what's seen in the laboratory, and doing the fits to determine the unknown coefficients. So you can see as we go to higher orders, we reproduce the data quite well. So this is at a lattice spacing of 1.3 Fermis. If we decrease the lattice spacing, things get a bit more accurate. Here's at 0.99 Fermi. The simulations get harder, but this is the direction we're going in to try to gradually decrease the lattice spacing. So now the calculations, well, maybe I should pause at this point and ask if there are any questions. Okay, I don't see any questions at this point, so I'll continue on. So we have these interactions on the lattice, but the reason we do this do the calculation on the lattices so that we can handle the many-body system. So the way we treat the many-body system is by doing Euclidean time projection. So that's where you do the exponential of minus h tau. So this is not real-time evolution, it's imaginary time evolution or Euclidean time evolution. So as tau gets large, what we're doing is we're projecting on to the low energy states of H. So you'll notice that the high energy states will get this exponential suppression. And so that's why the low energy states will survive the longest as tau gets large. Now, the Hamiltonian contains the kinetic energy term of the nucleons. If I insert the kinetic energy term, so we treat the nucleons non-relativistically. So H will have a kinetic energy term minus del squared over 2 times the mass, m. So if I do that exponential of minus negative del squared over 2m tau, that gives me a diffusion operator. And so just from the kinetic energy, we get a diffusion process. This diffusion can be modeled exactly as particles that are executing a random walk in space as a function of Euclidean time. So these particles and these nucleons are doing this random walk as a function of time. So here's this initial time tau equals to 0 and some final time tau equals to tau final. But there's also an interaction in H. So as these particles do this random walk in space as a function of time, they also have the exchange of pions, they have these short range interactions and so on. And so that's sort of a simple picture of how the quantum Monte Carlo works. And if you're familiar with diffusion Monte Carlo simulations done by people like Joe Carlson, Stefano Gandolfi, Alex Gitserles, they are essentially doing these simulations in this framework, where they have random sort of walkers that emulate the diffusion of these, doing the random walks of these nucleons. The way we do the calculation, though, is we take it a step further and we introduce auxiliary fields. So this is what's called the auxiliary field method, right? So we have these interactions, the exponential of this interaction term. So n dagger n squared is a two-body interaction. I said that we want to do the exponential minus h tau, so we need to do this exponential, okay? So we can write this term. So if I can think of n dagger n as some real variable, then I can just rewrite this exponential in terms of the integral of another exponential, but this time it will be a Gaussian function of this extra variable, this auxiliary variable s, integrated from minus infinity to plus infinity, where there's a linear shift in the quadratic form. Okay, so it's Gaussian, but with this linear shift. But you know how to do this integral. What you do is you complete the quadratic form to make it a perfect square, and the term that's missing is exactly this term here. And so if you do this integral, doing the integral will give you the factor of square root of 2 pi that cancel this factor here, and what remains will be exactly this exponential minus c over 2 n dagger n squared. So this is an exact transformation. The reason it's useful is that instead of having n dagger n squared exponentiated, we have the n dagger n just to the first power exponentiated. So we don't have two-body interactions, we have a one-body interaction. So if we now have this auxiliary variable at every point in space and time on the lattice, then we have simply the nucleons decouple from each other and simply they interact with this auxiliary field. So now what we do is we simply do a simulation where we sample this Gaussian random auxiliary field, and then by integrating over the auxiliary field, we reproduce exactly the interactions. Okay, so shown pictorially, it looks something like this. Instead of having what I showed before, the nucleons interacting with each other directly, what we have now is that the nucleons are individual nucleons interacting with the auxiliary field, which we can have an auxiliary field that doesn't care about spin or isospin. We might have an auxiliary field that depends on isospin. And then we also have couplings to the pions, which look a lot like the auxiliary fields, except for the pions have spatial correlations that give us the one-pion exchange interactions that give us these spatial correlations. So now what we have are these single nucleons amplitudes. So we have some initial nucleon J and some final nucleon I. So we will have a matrix of single nucleon amplitudes that will be a function of the auxiliary fields S, SI for the isospin dependent auxiliary field, and pi I for the for the pion fields. Now, to get the full many-body amplitude, we have to multiply these single nucleon amplitudes together. So if I have A nucleons in my initial state, this is an A by A matrix, and I will get the determinant of the A by A matrix. So what happens now in our supercomputer simulation is we do calculations of this determinant of this A by A matrix for every possible value of the auxiliary fields and the pion fields, and we do Monte Carlo sampling of those fields. So this is probably a good place for me to pause and ask if there are any questions.
So maybe inject one question here.
Sure.
Does this auxiliary field have a physical interpretation, or just this is just a numerical trick?
So it's a numerical trick, but the average value in some location of the auxiliary field can be interpreted as a mean field as well. So it has some significance in that.
So what is the, if you go back, when you do the integration, right, there's a range of the S variable you need to integrate. What is this, what's this range? Like, what's the length scale for this field, and what does that mean?
Okay, so
the project are interesting, for example?
You mean the limits of this integration?
Yeah,
or?
yeah. When you do the actual calculation, I mean, this probably there's a region where the integration is dominating, right?
Oh yeah. So there's this, yeah. So it'll be centered about some value that will be related to the mean field. So you know, so you can think of the nucleons as interacting with a mean field. So the local expectation value of S will be related to the strength of the mean field at that location.
Okay, and the width you need to.
Yeah, the width will be related to fluctuations. Yeah.
Sort of like the temperature of.
So these are zero. So very often we're doing zero temperature, like ground state calculations. So these are quantum fluctuations.
Okay.
Okay, very good. Okay, so now let me talk about.
I also, excuse me.
Sure.
I also ask the.
Sure.
Yeah, go ahead.
Slide. Maybe I can ask later. You see, you have a pion, but you don't have a sigma because you treat sigma as a contact interaction. But we know if a chiral symmetry restored in the nuclear medium, then sigma meson mass decreases, pion mass increases. Do you have the feature of a pion mass increases as you go into the medium? Yeah,
so we could explore explicitly the nature of the pion in the medium, but right now our pions are simply potential exchange pions. They're not dynamical pions. So we are working below the pion production threshold. So we don't have pions and such. But the reason we include so the sigma exchanges are, as you say, included in the short range interactions. But as I say, we don't actually produce any mesons dynamically. So that's
no, but even they are not produced. But they are even the virtual particles. They still have effect, right? For them, if you have sigma, if it's sigma mass changes, you affect the strength of such attractive interactions. I think that's what Edward Shur was trying to push, right? He said when nears the critical point, sigma mass become very, very small, and therefore the nucleon become very attractive.
Yeah, that's a very good point. So we have thought about doing such calculations of meson masses in medium, and we can do these calculations for sure. So we have all the correlations. So these are things we can see. But what we will need to do is we will need to actually have a world line associated with the meson. That's not in our simulations right now, but we have the correlations. So these effects that you're talking about should be something we could calculate, but we just haven't done.
But it's in your calculation. It's included dynamically.
Yeah, we haven't looked at it. Everything's there. We have all the physics there.
That's great. Yeah. All right. Thank you so much.
For sure. Yeah. Interested in So this was a project started by my former postdoc, Mingnan Liu, who's now a faculty member in Beijing. And we were interested in understanding the essential elements for nuclear binding. In other words, what is the simplest interaction that would do a good job of explaining the bulk properties of atomic nuclei? And so we found that that we could construct an interaction with only 4 parameters. Okay, so 3 of the parameters were fitted to systems with only 2 or 3 nucleons. So like the deuteron or 2 nucleon scattering, and the triton or helium-3. One of the parameters was fitted to everything else beyond A equals to 3. So the specific parameters that we played around with was the strength of the 2 nucleon interaction in the S wave, the range of the 2 nucleon interaction in the S wave, and the strength of the 3 nucleon interaction. The one sort of special ingredient that we threw in was the range of what's called the local part of the 2 nucleon interaction. This was something that was perhaps not very well appreciated before, but let me explain what I mean by local part. So when I say local, what I mean is an interaction that's diagonal in position space, in coordinate space. So for example, the Coulomb interaction is only a function of the positions of the particles, right? So this is what I would call a local interaction, whereas a non-local interaction is an interaction which could change the relative separations between the particles, right? So that could also be thought of as a velocity-dependent interaction. And so the local part is referring to specifically the part that's diagonal in position space. That seems to have an importance for nuclear binding. So anyways, the results turned out to be surprisingly good. So you can read more about this from this paper in 2019. Basically, so by fitting 3 of the parameters to data over here, the A up to 3 particles, and then 1 parameter to fit everything else, you can do a pretty good job of helium, beryllium, carbon, oxygen, neon, magnesium, silicon, sulfur, argon, calcium isotopes. There are clearly some discrepancies between the lattice calculations in solid and the experimental observed values in the open symbols, but the bulk properties are well described. So that was sort of kind of nice because these simulations could be done with no sign problem. There would be no cancellations of plus and minus configurations. These are purely positive configuration simulations, which is great for us. So the description of the binding energies are quite good. So we actually fitted Triton, so that's sort of cheating, but the rest are doing pretty well for this very simple interaction, as well as the charge radii are fairly well reproduced with this fairly simple interaction. Later in my talk, I'll show you results that are considerably better than this, but this is done with a very simple interaction. I think there's something in the chat. Let me see. So there's a question from Yin. Can one determine those model parameters from lattice-QCD? Yeah, in principle, yes. If lattice-QCD can do a good job of nucleon-nucleon scattering, so this is sort of the frontier of lattice-QCD to try to get the scattering properties of 2 nucleons. This turns out to be a fairly difficult thing to do, mostly because the binding is sort of what you do is you measure small differences in energy in a finite volume, for example. But those differences in energy are very small compared to the rest energy of the nucleons themselves. So that's why it's difficult. But yeah, hopefully in the next few years, some of these parameters could be directly determined from lattice-QC. That would be a very, very nice. Okay, so now let me talk about the pinhole algorithm that Zhang Yao mentioned. So we so somewhat different from other ab initio methods, we can actually now see where all the nucleons are using this thing that we call the pinhole algorithm. And so let me explain what is the pinhole algorithm, okay? So basically, so I have these equations here, but I think the easiest way to describe the pinhole algorithm is to just show you this picture. So in the beginning, I said that we have this Euclidean times, simulation. Here's the Euclidean time tau equals to 0 initial time, and here's the final time tau final. And so if this is a very large time, then in the middle of that simulation, on both sides of the midpoint, our quantum state is in some low energy eigenstate. And so we do essentially all our measurements in the middle of the Euclidean time simulation. We measure observables in that middle time slice. Okay, but what we're going to do here is do something quite special. We're going to have a brick wall that kills all the amplitudes, except for when the nucleons are positioned at these pinholes in the brick wall. Okay, so there's these little holes. These little holes are also have spin and isospin labels I and J. So if I have a simulation with 16 particles, there are 16 pinholes. So there's a one-to-one correspondence. And that's nice because the pinhole positions then give us the positions of the particles. So why are these pinholes useful? Well, we can now do Monte Carlo updates of the pinholes, and as well as doing the Monte Carlo updates of the auxiliary fields and the pion fields. And those pinholes give us a classical distribution of the particles. And what's really nice about this is they give us fully correlated distribution. So if we have an A-body system, we have two-body correlations, we have three-body correlations, we have A-body correlations in the data. Okay, and so we can measure straightforward quantities, again, using this fairly simple interaction. We can measure then the charge distribution of oxygen 16. You can see here at leading order in the red, when we introduce Coulomb using perturbation theory, it does a fairly good job of reproducing the empirical results from electron scattering. If we do the same for calcium 40, we have a little bit of excess of density in the center, but still it's doing a pretty good job of explaining or reproducing the charge distribution for this very simple interaction. Now, we can also take a look at what the actual pinholes look like. And so this is just sample configurations of our pinholes from the oxygen 16 simulations. And so these are configurations that I think we stored something like a few hundred, 30,000 or something like that. So you can see proton up, proton down, neutron up, neutron down. You can ask the question whether there are correlations like alpha clusters in this data. And the answer is actually yes. You can see this from our simulations. And so what we're working on now, I'll speak about that more in just a moment, is producing these pinhole configurations for the heavy ion, relativistic heavy ion community, so that you can use these pinhole configurations for your initial states for your hydrodynamics. Okay, so let me then tell you about some calculations I did with Jackie's group, doing oxygen 16 collisions at RHIC and LHC energies. So these collisions have been proposed at the LHC to probe the dependence on initial states of intermediate size. So these states are, oxygen 16 is expected to have some degree of alpha clustering, and that would be interesting to see whether the hydrodynamics from the heavy ion collisions is sensitive to that. Sorry, I didn't mean to do that. So now, one thing I should mention is that obviously, yeah, a question?
Yeah, can I ask a question? Can I
sure.
ask a question now? So going back to what you just showed before, these fluctuating positions of the nucleon. So these pinhole pictures can be interpreted as samplings of an underlying n-body, n-nucleon position probability distribution?
Yeah, they are exactly that. I skipped this page here, but this is exactly what's being measured. It's the normal ordered A-body density operator. That's what's being calculated, the expectation of that for the ground state.
Very nice.
Okay, yeah, great, thanks. Okay, so for oxygen collisions, the system is quite small. So, you might consider doing some oxygen-lead collisions to try to probe in a different way. But here we did the analysis of oxygen 16. So we are definitely pushing the limits of hydrodynamics. We're using the Vishnu package tuned to P-lead and lead-lead collisions at the LHC. And we use Trento to create the initial entropy distribution. Now, the entropy distribution, okay, so there's some details here I'm not going to go through because they're more experts on this than me. So I'll just tell you, so we compute the following cumulants for the flow harmonics Vn. So Vn2, that's Vn squared, square rooted, expectation value square rooted. And for the cumulant Vn4, we subtract V squared squared minus 2V squared squared minus V4 and take the fourth root. And we compare results taking the initial density as a simple Wood-Saxon potential, where we tune the density, the radius, and diffusivity to the empirically observed values. Then we consider the same Wood-Saxon potential, taking into account possible quark substructure of the nucleons. And then we use the nucleon distributions from the lattice-affected field theory calculations. And this is expected to incorporate correlations such as alpha clustering. So if we do have alpha clusters, the expectation is that the alpha clusters probably have some tetrahedral shape to them, some geometry like that, and you might see some deformations from that. So I should mention, how much alpha clustering do we see in the simulation? So we can just measure this from the simulations, the lattice calculations directly. So one way to do that is you can measure rho squared. So that's just the probability of having two nucleons very close to each other for oxygen 16 as a ratio of rho squared for helium-4. And so if we had very, very simple 4 alpha clusters, this ratio would be 4. But you may be puzzled why the answer is greater than 4. This is actually because there is alpha clustering, but the alpha clusters are overlapping with each other's, and so there's some entanglement of the wave function. So it's not a simple tensor product state of alpha clusters, but they're overlapping nucleons. So you can't say these 4 nucleons are part of an alpha cluster. What's really going on is this nucleon is actually part of an alpha cluster here, but it's also partially part of this alpha cluster. So there is sort of like this fluctuation of the alpha cluster wave functions. But you can see sort of at the 10% level, there is some interpretation that we have a significant amount of alpha clustering coming from rho squared, rho cubed, and rho 4. This is obviously measuring 3 nucleons being close together, 4 nucleons being close together. Okay. So if we then look at what the data looks like for at RHIC energies and for and LHC energies, 200 GeV and 6.5 TeV, let's focus here on V42 over V22. There is for central collisions, you can see there is some differentiation here. You can see for the Wood-Saxon is without the quark substructure is in the middle. If we introduce some quark substructure, it decreases V42 over V22. If we introduce the alpha clustering, then we go in the other direction. So you can think of this as the alpha clustering is somehow reducing the degrees of freedom. Instead of having 16 uncorrelated particles, we have more like somewhere between 16 to 4 alpha clusters, so some sort of reduction of the degrees of freedom, and that reduction give us more fluctuations. Sort of 1 over square root of n sort of scaling with the number of degrees of freedom. Whereas if you introduce the quark substructure, you're kind of you're decorrelating things more because you have more degrees of freedom. Now, maybe I should pause and ask if there are any questions at this point.
Yeah, I have a question not related to heavy-ion collisions. Since you said you have alpha cluster, if you pick up those alpha, one of the alpha cluster, you know the wave functions, although they are correlated. If you use that for wave of those 4 nucleons, 2 protons, 2 neutrons, they like alpha cluster. If you use the same interaction, you calculate expectation value. Does that alpha cluster have the right binding energy different from the free space? My point is alpha binding energy change in the median?
So I will talk a little bit more about this when I do the carbon-12 coming a little bit later, but the answer to your question is that they're very similar. They're very similar. So we don't measure the energy, but we can measure, for example, the matter distribution, the charge distribution of the alpha clusters, and they look very similar.
But in principle, you can also calculate the binding energy. right?
Yeah. It's a little bit more difficult to do that. We would have to measure then the expectation value of the local, sort of like the local expectation value of the energy. We haven't done that, but yeah, okay. I think you're right that we could do that as well.
Okay, thank you.
Sure.
Huichao, you have an immediate
I have a question. My question is your first principle calculation already indicates that there must be alpha cluster in oxygen, or there is still some uncertainties that you are not sure whether there is alpha cluster or not?
Yeah, so our calculations clearly show there is alpha clustering. The reason why there's an open question, I think, is because in other calculations, it's very, very hard to see this. So we have these configurations and we can look at it. The other methods usually are based upon some shell model orbitals. And when you expand in shell model orbitals, it's very hard to see this alpha clustering.
The question is, so there is still debates on the nuclear structure side whether there is alpha cluster in oxygen. So heavy-ion collisions for oxygen-oxygen collision in the near future can help us to distinguish whether there is such alpha cluster. Right?
Exactly. Okay. Yeah. So I think the relativistic heavy-ion collisions can give some information about correlations that are difficult in low energy experiments because it's hard to measure correlations, 2-body, 3-body, 4-body correlations in low energy experiments. So there's an opening here for relativistic heavy ion collision. You can do things like deformations, neutron skins, but I think clustering correlations is very much an exciting opening here for relativistic heavy ion collisions.
Oh, maybe you have a quick question, then we continue. Okay, go ahead, Wooly.
Yeah, looking at the left column, what's the origin of the huge difference in centrality dependence between 200 GeV and 6 TeV?
This side, let's see. So yeah, I'm not. This is outside of my expertise to know the differences, how this jumped from 0.25 to 0.45.
Well, that's not what I mean. I mean the shape as a function of centrality.
That's a good question. I also don't know that. This I would have to defer to my heavy ion collaborators who did these calculations. Yeah, I don't know that, Uli.
I will see them next week. Okay.
Okay, thanks. It's a great question, though. Okay, so now let me give you a sampling of other things that might be interesting. So I know the thermodynamics I'm going to talk about are not the energies at which most of you are working at, but actually Chimeng would be interested in this, so I'll mention this. So I know some people in the audience are very interested in this. So we are interested in ab initio nuclear thermodynamics, where we do calculations of the partition function. We can either work in the canonical or the grand canonical ensemble. So basically what we're doing in this case is we're using pinholes for the initial state and for the final state that are exactly the same, and then summing over all the pinholes. So what this is really doing is we're doing a trace over quantum mechanical states in position space, okay? And so that's how we're going to get our partition function in the canonical ensemble or grand canonical, depending on whether we change the number of particles in our simulation or not. Okay, so we can do these calculations and we can plot very interesting things like this, like the charge density distribution of oxygen-16 as a function of temperature. So you can see this simulation is done without Coulomb. So here is what we get compared with the empirical results. So without Coulomb, it's a little bit too high here, but that's because Coulomb is not included. But now we turn on the temperature. What happens is we see that this tail, there's a tail that appears. We interpret that as some of the nucleons boiling off the oxygen-16 nucleus and a reduction in the central density. We increase the temperature further, there's further reduction in the central density, but then the tail increases as well. So what's happening here is we no longer really have oxygen-16 as we increase the temperature, but probably we have things like maybe one or two alpha clusters remain, as well as a gas of nucleons, as well as maybe deuterons and tritons. Okay. So then we were interested in what is the behavior of the phase diagram. So again, I'm not going to be able to reach up here, but we can do the liquid gas, the liquid vapor transition near the critical point. And so we did some calculus. So this is again was led by my former postdoc Bingnan Liu. We did calculations of here's the reduced nucleon density. That's the density of nucleons divided by the saturation density. Saturation density being 0.16 nucleons per cubic Fermi. And so we see it about around half or 0.4 times the nucleon saturation density. We have this critical point here. You can see it for the chemical potential versus density or pressure versus density. So these are isothermal lines. Isothermal lines at temperature 10 MeV, 11, 12 MeV. And the liquid vapor coexistence line can be seen here. And then at the bottom here is the critical point. If we see the same thing in the pressure versus density, we get this point for the critical point, which is in pretty good agreement with at least some empirically extracted data from heavy ion collisions at these energies. So the critical temperature is about 16 MeV. Critical density is about 0.09 nucleons per cubic Fermi, and here's a critical chemical potential and the critical pressure. Okay. Let me ask if there are any questions about this.
What does if you come to even lower densities, then one should see the more formation of alpha clusters.
Absolutely, yeah, absolutely, and we do see that.
I think it was seen experimentally when you go to very low density, low temperatures, the matter dominated by clusters.
Yeah, in fact, so I'm part of this nuclear lattice-affected field theory collaboration, and Zhengxi Ren is listening to the talk right now, and he is part of the collaboration, and he's doing actual calculations of the cluster distributions as a function of density and temperature. So yeah, he has results on how many, what percentage of the nucleons are are single nucleons, what percentage are dimers, how many are trimers, how many are tetramers. And it's quite interesting what you can see.
That's right. Thank you.
Okay, so you can see also alpha clustering as a function of density and temperature. So here is rho to the 4, local rho to the 4 divided by absolute expectation value of rho raised to the 4th power. So a large value for this indicates clustering, alpha clustering specifically, okay? And what you can see is when you are above the critical density, the alpha clustering, this indicator of alpha clustering is somewhat independent of temperature and fairly low. But when we're below the critical density, we see there is a dependence on temperature and the signal is quite high. So at low temperatures and this below the critical density, as we decrease the temperature, we get more alpha clustering. As we increase the temperature, this starts to dissipate. So this is the signature of this alpha clustering. Okay, so now let me talk to you about this calculation of the spectrum, the structure and spectrum of carbon-12. And I highlight this because this just came out in Nature Communications yesterday. And so this was led by Shihang Shen, who's a postdoc with my collaborator, Ulf Meissner. All right, so what we did in these calculations was to try to pin down the actual structure of carbon-12, all of the low energy states. Now, there's a story behind carbon-12. If you haven't heard this, it's a really good story that, carbon-12 is clearly very important for the organic chemistry of life as we know it. But it's actually very difficult to produce carbon-12 because if we look at the binding energy per nucleon for the light nuclei, there's this big chasm between carbon and carbon-12 and the alpha particle, helium-4, in that you can't sequentially add a few nucleons at a time because that requires putting more energy in than you started off with. Okay, and so the way nature solves this problem is actually by having this triple alpha reaction. However, in massive stars, the problem is that having a three-body reaction like this is fairly rare. It's very rare. and it can't actually happen with sufficient frequency to explain the carbon in the universe. And so Fred Hoyle postulated the existence of this resonance of carbon-12 that sits close to the triple alpha threshold that would perhaps enhance this reaction. And so that's a Hoyle state, and so that's sort of, it was then discovered just a couple of years later experimentally. Okay, so we were interested in the structure of all these low-lying states of carbon-12. And so carbon-12 is sort of like the most interesting nucleus from the structure point of view because it's so weird, right? So here's then the ground state down here with a binding energy of about 92 MeV. So here, the experimental results are with the stars. And we did calculations using chiral effective field theory at next leading order and with the simplified SE4 interaction, and both did a pretty good job of reproducing the data, right? And so what the shapes are here, you'll see these equilateral triangles and these obtuse triangles, and what these shapes are telling you is the actual shapes of the alpha clusters of these states. So there's some that are equilateral triangles, there's some that are obtuse triangles. The interesting thing is all these states have one or the other. Okay, so let me show you the pictures of these states. So here's the ground state. We have 3 alpha particles, three alpha clusters. So this comes from the pinhole simulation. So we can actually see these intrinsic shapes. They have this nice equilateral triangle structure, whereas the Hoyle state is 3 alpha clusters in this sort of bent arm or obtuse triangle configuration, right? And there are other states that are in the same rotational band that have this equilateral triangle or the bent arm configuration. We did this calculation using the simplified SE4 interaction, and we also used the chiral EFT and two-low interactions. These calculations were an order of magnitude more difficult, so that's why these signals were more noisy. This is not an indication that the structure is really like messy or something. It's just that the statistical noise is much greater in these simulations. What's interesting is that the configurations that have these equilateral triangle configurations, geometries, also had a dual description in terms of shell model description. So whenever we saw these equilateral triangle shapes, we could also get a good overlap with shell model initial states as well. So there's this duality for these guys. Now, in the last part of my talk, I will talk to you about one of the drawbacks of these lattice simulations, namely the sign problem, and how we are now able to overcome these problems using a technique called wave function matching. So these lattice Monte Carlo simulations can compute these non-trivial correlations in nuclear many-body systems. Unfortunately, sign oscillations prevent direct simulations using our best interactions. So N3 low next to next leading order with a short lattice spacing has these short range repulsions that give us these sign problems. The way we solve this problem is using a technique called wave function matching. And let me try to explain what the technology is. So we have this set of easily computable Hamiltonians that don't produce a sign problem. The problem is that we actually want to do a Hamiltonian that sits over here where we're not very close to the set of easily computable Hamiltonians. But what we can do is we can do a unitary transformation that changes the interaction but keeps the actual S matrix elements for the nucleon-nucleon phase shifts the same. So we get a new interaction H prime, which is just as good as H, in some sense, just completely equivalent in terms of quality, but it's close to these easily computable Hamiltonians. Then we can use first order perturbation theory, or later, if we want to go to second order perturbation theory, we can then do these calculations very accurately and efficiently. Now, how do we do this transformation to go from H to H prime? This is the technique wave function matching that's described in this paper here. Okay, so here's, let's say, the scattering wave function or bounce it, depending on whatever the channel is. We have the wave function, the radial wave function for some for some difficult Hamiltonian H, okay, that let's say has some short range repulsion. Then we have the ground state wave function for our simple Hamiltonian, let's say H for H simple or H L for low fidelity or simple. And then we have what wave function matching does is it keeps the part of the wave function that is beyond some radius capital R, it keeps it exactly the same. It doesn't touch that. But it does some finite range unitary transformation. It does plastic surgery to remove the short range part of this wave function and replace it by the short range part of the simple interaction. But because it's a unitary transformation, it can't change the normalization of the short range part. So it's off by some factor. Okay, it's rescaled by some factor. But because this new ground state wave function is very close to the wave function of the simple interaction, the ground state of the simple interaction, first order perturbation theory works beautifully. And that's how this all works. So let me just show you again. We have some initial interaction Hamilton HA, and we do a unitary transformation of unitarily equivalent Hamiltonians, and then we picked some interaction HA prime. And then this allows us to do the first order perturbation theory to get that calculation to work. So let me just do a very simple example. We have some repulsive interaction VA that has some repulsion. So the reason why I have these bars here is because this is on the lattice. There are only certain discrete values of the lattice, of the distance here. So we have repulsion here. For VB, we have an interaction that's very easy for our Monte Carlo simulations with no repulsion. Okay, so they produce different phase shifts. For VA, the phase shift, the S wave phase shift crosses zero as we go to high momenta. That's an indication that we have short range repulsion. If we now look at VB, it never crosses zero because there's no repulsion. Okay. All right, but now let's do something very simple. We take the eigenstates in some two-particle channel for HA and for HB, psi AN and psi BN with energies EAN and EBN. K will be our kinetic energy, and VA, VB I defined before for the interactions. Now, we would like to compute the eigenenergies of HA. We want to get these energies by starting from the eigenstates of HB, and then just using first order perturbation theory. If we could do that, that would be really convenient. Okay, so let's try that. And not surprisingly, it doesn't work very well. I take these are the exact eigenenergies of HA, okay, EAN here. And here are the eigenstates of HB, and I'm doing the expectation values of HA. And you see they don't work very well at all. This is not what experimentalists would like to see in terms of theoretical predictions. So, but what we can do now is use wave function matching. So we take the projection operator P, that's only non-zero for short distances for R less than capital R. And so that's this short distance projector. So I'm going to take the short distance part of the ground state wave function for HB, so that's psi 0b, and I'll normalize it because I need to construct a unitary transformation, so I need normalized states. And then this unitary transformation A will map this short distance part of ground state of HB to the short distance part of HA, normalized again. Okay, the rest of U is actually irrelevant, is not so important. There are many, many choices that you can take for U, but this is the essential ingredient, that this short distance part of psi 0b must map to the short distance part of psi 0a. And now what we're going to do is we're going to define this unitary transformation for the Hamiltonian. So HA prime will be U dagger HAU. So what is this U doing? It's making it, it's essentially translating the Hamiltonian such that the eigenstates of HB will be very happy for this HA prime. So, right, just think about what U does. It goes from the ground state of psi 0b to the ground state of psi 0a, and that primes it for HA, and then I convert it back to the eigenstates of HB. All right, so this is the new interaction HA prime. If I subtract off the kinetic energy, this will be our new interaction. And so this new interaction VA prime will not change the phase shifts because I only did a unitary transformation. So they have exactly the same phase shifts, all right? But it will do the following to the wave function. So here was my psi A ground state. Here was my psi B ground state. And so what happened was the tail of psi A remained exactly the same here. But I did plastic surgery and took this part of psi B and just did a pasting of that here, normalized to keep the same normalization, but this is what psi A prime looks like. And because psi A prime looks so similar to psi B, first order perturbation theory will work. And so we can check that this in fact does work. If I use HA prime rather than HA, then starting from the eigenstates of psi B, eigenstates of HB, first order perturbation theory does a really good job reproducing them, the energies, quite well. So second order perturbation would agree to 3 or maybe, at least 3-digit precision for all these energies. Okay, so we can now apply this to Chiral effective field theory at N3LO, which we could not do before using wave function matching. So here is the phase shift. So we do a good job of reproducing the phase shifts for Chiral effective field theory at N3LO. And then here are the results. So we can now reproduce the binding energies of all these nuclei up to calcium 40. We can go beyond calcium 40, but that's the focus of this paper here. And here are the Hoyle state and the ground state and the first 2+ state of carbon 12. So we can get the excited states pretty good as well as the neutron-rich nuclei. And what's really cool is we also can get the radii quite well without tuning anything to radii. This is actually quite challenging for ab initio calculations, but the radii come out right, suggesting that we have a pretty good description of the forces of nuclear, of binding forces. So we also have a good description of neutron matter. So here's neutron matter that we get for various numbers of nucleons. 14, 28, 42, 66, 80 nucleons. This is the energy per particle versus the binding energy, versus the density divided by neutron saturation density. We also have the symmetric nuclear matter with the same number of protons and neutrons, and we do a fairly good job of reproducing the empirical saturation point here. Okay, and so let me then just wrap up by giving an outlook. So this was an overview of some of the current capabilities of ab initio nuclear structure calculations, and I emphasize the work that we're doing with the nuclear lattice effective field theory collaboration, and it talked about how they can interface with studies of relativistic heavy ion collisions. So now, over the next decade, at least, it will likely be possible to do ab initio calculations of nuclear states across the entire nuclear chart. I'm pretty confident about that. There are many groups working on this using different techniques. And so the question now that we're leading into the discussion part would be, what interesting problems can the nuclear structure community and the relativistic heavy ion community address together in the future? So I'll end with that question, and I thank you very much for your attention.
Thank you, Dean, for the really exciting talk. So we already have some discussions, but please raise your hand. Yes, so that's not okay. Applaud. Okay. Is Xu know? I don't know.
Hi, I have a problem here. From my point of view, I think wave function matching is a little bit like advanced continuation. Can you explain the difference and the similarity of these two methods to me?
Yeah, so eigenvector continuation, those of you who are not familiar with eigenvector continuation, that's where we take snapshots of the wave function for some values of the coupling. We use those as training vectors and then solve the generalized eigenvalue in a reduced space that allows us to get energies that we have not calculated before. And this is very nice because we can do extrapolations to regions that we didn't explore. And we can have a fast emulator to calculate things as a function of many parameters. So eigenvector continuation allows us to go beyond perturbation theory. So wave function matching has a similar feel to it, but in wave function matching, it's more, wave function matching is to try to make one Hamiltonian look closer to another Hamiltonian. So in other words, what wave function matching does is something that I call a Hamiltonian translator. A Hamiltonian translator is a unitary transformation that does the following. Let's say I have HA and HB. The Hamiltonian translator is something that constructs a new Hamiltonian HA prime, whose energies are exactly the same as that of HA, but whose eigenstates are that of HB. It's translating from one to the other. Okay, and you can actually construct an exact Hamiltonian translator on a quantum computer using adiabatic evolution. So if you're not familiar with what adiabatic evolution is, you just do time evolution, where you start off at t equals to 0 with the Hamiltonian HB, and then you very slowly change the Hamiltonian to HA. So if I do a time evolution from HB to HA, then I hit it with HA, then I very slowly do that evolution back to HB, then this will be this unitarily transformed Hamiltonian, which I call HA prime, will have eigenstates of HB, but will have eigenenergies of HA. And that's actually what wave function matching does approximately.
Okay, thank you.
Sure, great question.
Okay. Aisha, go ahead.
Yeah. Thank you. Okay. Yeah, I have two questions. One is about the wave function matching method. You mentioned that it's using unitary transformation. So my question is this unitary transformation will induce some like three-body force or three-body Hamiltonian?
Yeah, great question. So yes, it will induce a three-body, four-body interaction. What is quite interesting, though, is the induced three-body interaction is very small. We've actually explicitly looked at this question now. Our paper is under review for a journal, and we've been exploring this very, very carefully. And what's interesting is that how should I say it? So wave function matching really only changes a very small piece, a short distance piece of the wave function. So as a result, the induced three-body interaction is suppressed because of the fact that we have soft interactions and the transformation is only changing the wave function in a small region. And so there's some suppression of the induced three-body interaction. But we take the point of view that we don't actually care about the original Hamiltonian. So in other words, what we do is we say, okay, we have HA, that's a chiral effective field theory. We have HA prime, that's another chiral effective field theory because it's a finite range unitary transformation. So HA prime is just as good as HA. So we don't actually calculate induced three-body interaction. We simply fit the three-body interaction for HA prime as though it was itself a honest to God chiral effective field theory.
Okay, I see. Thank you. I have a short another question. It's about you mentioned it's I think a lattice EFT also can do real-time evolution calculation.
I wish we could do that, but that's why we are working on quantum computing. So my research group, we do a lot of quantum computing as well. And so the classical simulations cannot do real-time dynamics, but we are working on methods to calculate spectral functions. So to do spectral functions in finite volumes, if you measure spectral functions accurately, then you can actually look at the distribution of the spectral density and measure widths of peaks. And from widths of peaks, you can get things like resonance widths. But in principle, if you look at continuum state widths, the spectral density in a finite volume of a continuum state, you can actually measure cross sections in principle from that. So we are working in this direction to try to get sort of quote unquote real-time dynamics from spectral densities, from spectral functions.
Okay, I see. Interesting. Okay, thank you.
Sure.
Okay, are there other questions?
Yeah, I missed something chiming here. Why you mentioned you introduced the wave function matching method? You said that when you go to NL3, you cannot do the usual calculations. Therefore, you introduce this wave function matching. What part of NL3 compared to NL2 which makes this happen?
Yeah. So great question. I didn't really talk about that. So at N3LO, we also decreased the lattice spacing to 1.3 Fermis. So we see more of the repulsion. So the N3 low calculation has more of the repulsion, more of the tensor force, and these cause fairly severe sign problems. And so the N2 low interaction with a somewhat larger lattice spacing prevents some of these sign problems from killing the simulation. But with the N3 low, with smaller lattice spacing, the wave function matching becomes necessary.
So as you go to high order, there are more repulsion at the short term.
Yeah, exactly. Yeah.
I see. Yeah. Let me continue. Can I ask another question?
Sure, sure.
I think your slide 42, if you can go back to slide 42 about the alpha clusters and also the shell model. That's one. You see, there are strong overlap of those alpha cluster configuration with the shell model of those wave functions, right? Yeah. So that reminds me a talk I heard from someone. They do the normal Hartree-Fock calculations in some interactions. They can get the oxygen 16 and the carbon 12 and so on. Of course, normally we'll never look at the alpha structure in those nuclei in the mean field approximations. But somehow this person, she borrowed some methods from chemists, people in chemistry. There's a way to look at the wave functions in the coordinate space. And she showed us indeed in radian 80 you have 2 alpha clusters, in carbon 12 you have 3 alpha clusters. I think that's exactly what you are saying, right? Even you shell model wave function.
Absolutely.
It's hidden there, but you don't see it if you don't look closely. But
that's right.
Your pinhole method, you can see it.
Yeah, exactly right. Exactly right. Yeah.
Now, if that's the case, of course, it's nice to be able to do up initial calculations. On the other hand, if we can also use the traditional Hartree-Fock calculations, then we get it. Normally, we just use the one-body density distribution to look at coordinate space distribution of the nucleons. I think that was the mistake. Therefore, we'll never get alpha clusters because in the mean field, normally we're interested in density, one-body density. But if we have a way to look at the underlying spatial distribution of the nucleons, one can also get alpha cluster even in the mean field level. Then we can initialize that for heavy collision as well. So the question is how important, but you have multi-particle correlations in your calculation, you have all the correlations. So how, in other words, how large is the overlap for them for your 3 carbon 12, the overlap of your wave functions to the shell model wave function? How large are the overlap?
Yeah, I understand what you're asking. So this will depend a lot on our resolution of the forces, but for this simulation, probably at the level of, if we take some fairly simple shell model wave function with our ground state, probably the overlap is 5% or something like that.
Oh, very small.
Yeah, it's very small because there are correlations now. But the overall structure, they look similar, but it's just because it's a very large dimensional space. The actual inner product will be small.
Yeah, but eventually, if you use this as the initial state for the relativistic heavy collisions, and you only look at the coordinate space distribution, or suppose I want to use I use that picture in the first row, right? That you as your initial conditions, that how to distribute in the space. Then that you as initial state for relatively heavy collisions. And it doesn't matter how you generate those distributions of the alpha cluster, whether they come from shell model or from your initial calculation.
That's exactly right. So the actual overlap at the wave function level is not really the important thing. It's the density distribution, the intrinsic shapes that matter. And at that level, the shell model calculation, as long as you do a good shell model calculation that gets an oblate ground state for carbon 12, it probably also has this triangular shape, so and some alpha clustering. So that's probably all good.
Okay.
Yeah, so my question is, how do we introduce the multi-particle correlations in your model as the initial state for the relatively heavy collisions, But normally, initial state, we do not know. We don't talk about multi-particle correlation. We only say what the spatial distribution.
Okay, yeah, but the way this works is we are giving these, we have these configurations that you can simply sample, and that allows you to do the initial states for the heavy-ion collisions. You just give this directly.
Or you give them directly all your wave functions.
Yeah, that's right. Yeah.
So let's take a question from Thomas.
Hey, Thomas.
Yeah, hi, Dean. I'm sorry there's noise in the background. Somehow I'm at home and there's a contractor in the building. I always wonder a little bit to what extent we understand kind of conceptually what we're doing when we sample these classical and particle configurations. I mean, take an extreme example, take a deformed nucleus, you know, uranium. Then what we use for a heavy ion collision is an intrinsic frame distribution, not a ground state distribution. And that seems correct, but I always wonder how well we understand exactly why it's correct and what the corrections actually are.
Yeah, so it's clear, right? So what we're really measuring, if we have a deform, let's say we have two nuclei that are the same nucleus, so they're deformed the same way, right? Let's suppose they're prolate deformed, and so we will have collisions where they hit side to side, head to head, right? So we will see fluctuations from event to event that will give us some indication that there is this deformed shape. So if we were just to rotate this spin zero state and say it's a spherical distribution in the laboratory frame, then that's clearly not going to reproduce this effect. So it's really the correlations of the structure of one nucleus with itself and one nucleus with the other nucleus that gives you the information. So it's correlations within a nucleus as well as nucleus with the other nucleus that gives us this information.
But is it really precisely the intrinsic frame distribution, or it should actually be smeared?
I suspect it really is intrinsic frame distribution to the extent that in the heavy ion collision, when they get smashed together, you're really taking you're collapsing the wave function in position space, because the nucleons simply get vaporized and they get converted into gluons and what else, right? So the only information is essentially the energy distribution that you had from the nucleons. So it's really a collapse of the wave function. It's picked some intrinsic frame, so for a given event, it has collapsed. And those are the positions of the nucleons. So that's the way I think of it. It's a measurement in position space.
Yeah, I mean, that's the hand wavy argument that we're using. But I wonder, I mean, for example, if you were to reduce the energy, it would be less and less true. So there should be some way to actually compute the error that you make.
Yeah, now I understand what you're saying, Thomas. You're saying, what is the systematic framework in which we say what is the correction in going from intrinsic frame to the laboratory frame as a function of energy? Yeah, I think we could try to work something out like that, because definitely for low energy collisions, it is the laboratory frame that matters. You know, the fact that you have a spherical distribution will matter at low energies for sure.
And you could ask similar questions about other things, like, you know, the quadrupole moment of the deuteron. You know, does it matter or does it not matter? In what frame should you be measuring this?
Yeah. That's a very good question. I like where you're going with that.
But
all these issues that we consider to be sort of philosophical issues are really quantifiable. You know, we can actually say how much is it intrinsic, how much is it laboratory, and what it was the proper framework in which to talk about these things.
Yeah. Okay, so are there okay, so maybe I ask a question. If you go back the pinhole, right? Yeah. I could imagine that you have some intrinsic resolution, like the size of the hole, right? I mean, there must be some kind of uncertainty in the position itself.
Yeah.
What is the uncertainty? Let's see, in your lattice simulation, like you know, in the energy scale you're talking about, what is the uncertainty of this position of the nucleons?
Yeah, so this is the data being shown here is at 1.3 Fermi lattice spacing. So that is the resolution. So yeah, we have this resolution coming from the lattice spacing. Now, in order to not have the lattice spacing be an artifact in the hydrodynamic simulation, what we've done is we've done some, random sort of noise that's added to remove that sort of alignment to the lattice grid. But so if you're asking the question, what is the effect of the resolution scale in terms of what we see from the hydrodynamic simulations? I think one can do. So there, for example, you might be wondering about the short-range correlations. How important are short-range correlations in the nucleon-nucleon interaction for the hydrodynamics of results? And so there is some effect, but there may be ways of removing the dependence on short-range correlations from doing ratios again, just like you've done to get ratios of isobars. Similar things can be done to try to remove short-range correlation effects. And I know Giuliano showed me some results where taking ratios for neon 20 and oxygen 16 could seemingly remove these short-range correlation effects.
Right. Yeah. I mean, basically, this pinhole is reliable for the long-range structure, but of course, also medium range maybe. So, but in the heavy-ion collision, let's see, when we take a very snapshot, a very short time scale, right? There will be a fluctuation, additional fluctuation, because I could start, it's not like a smooth quadruple shape, right? Even for uranium, if we do a sampling of the nucleons, we will have additional fluctuation in a very short time scale, right? This will play some role in driving the flow fluctuation, for example. Central region. I mean, even if you start with spherical system, after sampling the nucleon, you will get a quadruple, right? A small quadruple component. So I just wonder, this component need to be. I mean, what we are doing now is like a very simple. We just trust global model, right? But this may not be the correct way. I mean, the long range part we can get from you, which is quite good, but then. There will be additional fluctuation even on the nucleon level, which need to be included somehow.
I agree that once we have things like the long-range correlations under control, then we can look for signatures of these fluctuations of things that are happening at shorter length scales. This would be quite nice.
Yeah. Are there more questions?
Yeah, let's back to the same question, right? So you say really what you're interested in, forget the short range correlation now, just the long range part. You want to see what's the spatial distribution of the incoming nuclei, right? Inside the incoming nuclei. Then of course, if oxygen 16, you may have a 4 alpha cluster there, right? Now you can get this kind of initial calculations, and also it's you can get also from normal mean field Schermer-Hartree-Fock calculation. You also get those. If you look at spatial distribution, there are also 4 alpha particles. Now we know how to get them. Then the questions as far as that spatial distribution of those alpha clusters, they are similar. And so in this respect, I mean, it's nice to do those initial calculations, but the effect is similar if I also do it with the Schermer-Hartree-Fock calculations, for example. I get from the mean field level, get orbit. Then I look at the spatial distribution, I also get the 4 alpha clusters, as I just mentioned. Some people recently has achieved that already, right? So the question is, how do we go beyond that mean field level? I think that's the advantage of this kind of initial calculation. We have a multi-particle correlations. How do we? That will affect the heavy-ion collisions, and that part is the one thing missing from the mean field dynamics calculation for initial structure of the nuclei. And normally, short-range correlation only affect the momentum of the nucleons in the incoming nuclei. But the ultra-relativity, I don't care about those sheltering, the high momentum tail. Right? In the low energy heavy-ion collision, high momentum important, but in the ultra-relativity high momentum tail, not irrelevant. Right? The energy scale just cannot be relevant for those low high momentum tails. So I still don't see how to see anything go beyond the midfield level.
But Jimmy,
to see the different relatively heavy collisions. Yeah, go ahead.
I'm confused by your comment. I mean, of course, in the momentum space you don't see, but you could have two nucleons where just get very close in the space. That will have a consequence in the heavy-ion collision, right? In momentum information you don't, but if you have a pair of nucleons which are very close in space, they will influence the energy deposition in the heavy-ion collision. You will see that. That's the consequence of the short-range correlation, but it's not the momentum information you care about.
Yeah, that I agree. Yes, yeah. So for the your prepared initial state, right? So I give you the one body density distribution, two body density distribution, three body density distribution. How do we put that information into the initial condition of the nucleus before they collide? And I think that's we have to think our way of doing it, right? Yeah. Maybe one can sample them. We throw the initial distribution according to the one body, two body, three body distributions. Sample them. So in all the collisions involve all kind of distributions. So of course that will go beyond what we can do with the mean field. Then I agree. Maybe once we get it from the multi-particle nucleon distributions, then we just throw dice somehow to find all possible kind of spatial distribution of the nucleons, including those correlations as the initial conditions. So that's probably the way to make use of the information we learn from this kind of stuff.
Right.
For example, if a demon maybe can tell us, right? Suppose if RHIC 16, you have this fluctuating 16 nucleon, right? And we have to any kind of these pictures may be one of the initial conditions, right?
Mm-hmm. Yeah.
So we have to sample all of them. Or suppose do 1 million collisions, and then you have to using each one come from one of that picture you have. And do the collision and do another one, do 1 million, then see how that affects the V2 or V3 and so on and so forth. Was that the way done in your collaborative work with those heavy-ion people?
Yeah, this is what we did. Yeah.
You did it for each picture, then you do one calculation, another picture, you do another calculation. That's exactly what you did.
Yeah, that's what we did.
See. I see. Okay, so you have done that already.
Yeah.
Now, suppose that would be interesting. Now, suppose I do the same thing with the mean field model for the initial nuclei. Now, of course, I don't have this complete picture anymore, right? Then let's see what's the difference between the two. If the two has a large difference, then will be interesting. If the difference is very small, then we don't learn too much.
Yeah, it's very good. Very good idea.
Yeah. Okay, I think we probably run out of time now. If there are questions, well, people can still stay to ask a question, but we probably can stop the recording. Dean, just one last question I have. Like this Euclidean time projection method, are there applications in atomic or molecular physics? Like, are there people using this to do imaging of the theoretically using to image the position of the let's see, the electrons in the molecules, for example? Are there ways to study the image of multi-electron system?
Yeah, in principle, so the Euclidean time method is used for many body calculations. Quantum chemistry, for example, atomic systems, ultra cold atoms. A lot of simulations have been done this way. One challenge, though, for atomic physics is very often the Coulomb interaction is very important, and the calculation, the way I did the calculation, is not especially the lattice is not what quantum chemists probably would want to do. They want to probably work directly with orbitals. And so there's a little bit of a mismatch of the way we do the calculation and the way they want to do the calculation.
I see. Very good. So let's thank Dean Lee for this very good talk and also the very good discussion. And
thank you.
So I would say, leave this to the chair.
Thank you very much, everybody. Thanks for coming.
Yeah.
Yeah.
Take care.
Bye-bye.